Let's look at one problem for the bundle of tubes that have been arranged in a form of heat exchanger. We have air at 1 atmosphere and 10 degrees centigrade flows across a bank of tubes, 15 rows high and 5 rows deep, at a velocity of 7 meter per second, measured at the point before the entering the tube bank. The surface of tubes are maintained at 65 degrees C. Diameter of tubes is 1 inch and they are arranged in line manner so that the spacing in both the normal and parallel direction to the flow is 1.5 inches. Calculate the total heat transfer per unit length for the tube bank and the exit air temperature. So what we have here is arrangement of these tube banks in an inline manner. So we have 15 of them on top of each other. So the number of tube in the transverse direction is 15, and then these numbers are just repeated for 5 of them. So along the direction of fluids, we would have the NL5. So we have 5 of these rows of each 15 tubes, and there is air flowing in through this tube bank, and the air could be supplied by a fan or something like that. Velocity is 7 meter per second, and the temperature of air is 10 degrees C, which is equal to Ti. This is the temperature at the entrance, and the air would take out some heat. So it could be well defined for a cooling process. Let's say there are this hot water just flowing through the tube, and then we have this cool air just flowing outside and then cooling the water inside. But this is the focus of here is the heat transfer that happens in this tube bank outside for the air. So SL is 1.5 inches, 3.81 centimeter. The same thing with the ST is 3.81 centimeter for this tube. The surface of the tube are constant temperature of 65 degrees C. That's the arrangement of the tube, and we have an inline tube. So that's for that part. The knowns, if we list what we know about this problem, knowns, parameters that we know. So first of all, we know the temperature that air is flowing. The inlet temperature is going to be then 10 degrees C. The surface temperature is 65 degrees C. We know diameter of tubes is 2.45 centimeter, 1 inch. ST is SL 3.81 centimeter. Number of tube normal to the flow are 15. Number of tube parallel to the flow are 5. And air pressure is 1 atmosphere and velocity is 7 meter per second. So these are the list of known parameters. In terms of assumption, we can assume we have a steady state condition and negligible radiation. What else? We're going to assume uniform outer surfaces and uniform temperature at the outer surfaces. And another assumption that we can verify later on is negligible effect of temperature change along the tube bank on air properties. And what we have been asked to find is Q and T of exit. So air is flowing in, going out, taking out some heat from these hot tubes, and we are going to find out the rate of heat transfer for this tube bank. So the first step is to find out the properties. Now, we don't have really the air property, like we're going to find out the properties at the average temperature between Ti and To. But right now we don't have To. So what we are going to do, we are going to just stick to Ti. It's going to take out some heat and go out. But later on, we can evaluate that one. However, we are making these assumptions too. So using these assumptions that the air properties does not change along the tube. So the first step, air properties at 10 degrees C from table A4, we can read the properties. Kinematic viscosity of air is 14.2 times 10 to power minus 6 meters square per second. Prandtl number is 0.712 and K 0.0249 watt per Kelvin. Density of air is 1.2400 kg per cubic meter. Cp is 1006.66. This should be in joule per kilogram Kelvin. And another property that we need is the Prandtl at the surface, which is the Prandtl number at the temperature, Prandtl number of air at the surface temperature, which if you read it, is gonna be 0.7. So this is the first step. Second step is finding H average. So if the number of tubes in the longitudinal direction is less than 20, then we have a correction. So what we use is the Nusselt number D for n less than 20 and L less than 20 is going to be C2 for the Nusselt number D, the one that we have seen for the larger one. So n, let's say, greater than 20, and it's going to be C2 C1 Reynolds number of D and max to the power of m, Prandtl number to the power of 36, and then we have a correction factor PR taking account the effect of surface temperature PRS to the power of 1/4. Now the number of tubes along the flow directions are 5, so NL is 5, and then for the aligned tubes, what we have is from table 7.6, C2 is going to be 0.92. Reynolds number D and max is maximum velocity that can occur in this tube bank, D divided by kinematic viscosity. Vmax for an inline arrangement, for a square arrangement, is ST2 SD minus D times the inlet velocity. So it's going to be 3.81 to 3.81 minus 2.45, and the velocity is 7 meters per second, so we're going to get 21 meters per second. So this is the maximum velocity, 3 times more than the inlet velocity. So the Reynolds of D and max would be this 21 meters per second times the diameter 254 14.2 times 10 to power minus 6. We're going to get 37,563,000. So this is the Reynolds number. By having the ratio of ST over SD, which is here 1, that's greater than 0.7. And for the aligned arrangement, we can go to the table 7.5, and what we are going to find is C1, the parameter 0.27, and the exponent for the Reynolds number 0.63. So having that one, now we can evaluate the Nusselt number. So Nusselt number of D average for n greater less than 20 is going to be 0.92, which is C2, times 0.27, which is C1, times the Reynolds number, which was 37563 to the power of 0.63. Prandtl number is 0.712, and the correction 0.712 divided by 0.7 to the power of 1 over 4. So Nusselt number, if you do the math, it's going to be 189.98. So from here, we can get the H average equal to the Nusselt number of the average. So here, our H average is going to be 189.98 times 0.0, oops, sorry, times K. K is 0.0249 and D is 0.0254. So the number is going to be 186.3 watt per meter Kelvin. So this is the average heat transfer coefficients that we have along this tube bank. That's step 2. So we got the properties, we find H average, and then the other one is, so we need to find the fluid temperature leaving the bundle, and for that one we have the formula Ts minus To, Ts minus Ti, and that's based on the energy balance exponential of minus pi dNH average divided by rho VCP NTST. And these properties are at free stream temperature. So Ts is 65, To we don't know, T is 65, and T inlet is 10. Would be exponential of minus pi. D is 0.0254. The total number of tubes are 15 times 5, that's N, and the H average is 186.3. Density is 1.2400. Velocity was 7 and CP was 1006.66. NT was 15 and ST was 0.381. So this is going to be exponential of minus 0.223274, and from here T0 is 65 minus 55 times this exponential, which is 0.799895, and the value of TO is going to be 21 degrees C. So this is the outlet temperature. Now we can look at the delta. If you look at the Ti minus To, the difference is Ti was 10 degree minus 21 is 11 degrees C. Now, this is what we can say, this is so small that, or the other way that you can look like this T average, Ti plus To divided by 2 is going to be 10 plus 21 divided by 2. 15.5 degrees C. So the right way of continuing here is to go evaluate the properties as 15.5 degrees C for the air properties and repeat the calculations. And repeating this process till we average to an outlet temperature that does not change. However, since the change, like we evaluate the properties at Ti is very close enough, like 15.5 is close enough to 10, that we can say it is appropriate to use their properties as 10 degrees C and continue with the calculations that we have had. So this is, I'm gonna say, close enough. Oh, or Ti is close enough to this T average. So assuming that the properties does not change, or we have a little change is okay, or evaluating properties at the inlet temperature is okay. Now, the next step, having Ti and To, we need to find out what is the temperature difference, like some average form of temperature difference between the tube bank and the flowing air through the tube bank. And therefore, a bank of tubes, what we were using was this log mean temperature delta TLM or LMTD, which is TS minus Ti minus TS minus To, natural log of TS minus Ti, TS minus To. And this is going to be TS is 65 minus 10, 65 minus 21, 5 minus 21. And if you do the math here, we will get 49, 29, 562. That's the degree C. So that's the delta T that we are going to use for evaluation of heat transfer rate. Note that, at the inlet we have air coming at 10 degrees C. So the temperature difference between air, so let's say if this is the tube bank that we are looking at. So the air that is getting in is 10 degrees C. When it's going out is 21 degrees C. Now the tubes are at 65 degrees C. If you use the inlet temperature, the delta T is going to be 55. If you use the outlet one, it's going to be 44. Now, what we need here is an average, and then from the energy balance equation, that was the average that we were getting for the temperature. So instead of either of them, we're going to use this number for calculation of Q in the next step. So the heat transfer rate per unit length, say this Q prime is going to be Q over L, and that's going to be H average surface area, which is pi d times the number, okay, per unit length times 1 actually, delta T Lm. So we have the 186.3 pi times 0.0254 times number of tubes 15 times 5, and the temperature that we're getting is 49.29562. And if you do the math, it's going to be 54962.4 watt or 54.9 kilowatt. This is going to be the rate of heat transfer per unit length of tubes in this heat exchanger or in this bank of tubes.